So if you're at the top level stream right now, just add another calculation. Okay, double click on add stream. And let's just call this one bubble point. Okay. Just a second here, I want to make sure I get the right thing up and running. Second, I'm trying to find the case file. So I'm doing the right one with you. Oh, okay, good. Bubble point, good. All right, what we're going to do is we're going to add acetone to the grid. So again, we're going to just keep on working with the default settings, and at least for the first calculation. Then we're going to make a change in just a second. So type in acetone here. Okay. And for now, just add the amount of, let's just add 10 moles of acetone to this. We're actually going to change that in just a second, but I just want you to stick with the same units for now, and then we're going to start looking at other units. So add acetone in 10 moles to this water. Okay. And just to make it easier for you to look at, set the water to 40 moles. Okay. So now we can see we've got a system that contains a total of 50 moles, and it's roughly 80% water. I want to make sure that everybody is now in MSc. So I think it was you, Brett, right, that was working in AQ initially? You have, is your next calculation showing MSc?
No, no, I'm in MSc.
Perfect. Okay, good.
Wow.
Okay, good. Now that we've got our stream set up, right? We've created the contents of the stream at 20. It's at 25 C in 1 atmosphere. Okay. What we're going to do is we're going to add another single point calculation. So add calculation in the upper right, single point. Okay. Again, all the contents from here makes it down here. On the right-hand side, once we add the single point calculation, our first thought is, let's go to the right-hand side and see what kind of calculation we want to do, or hit the calculate button, and also look in our summary section to see what's being done. Okay, so add a single point calculation, look over to the right. Now what I want you to do is just click on that drop-down arrow. There should be, what, 13? I think they're 13, 2, 4, 6, 8, 10, 12, 13 different types of calculations. Single point calculations that are available to you. We just ran the isothermal one. The one we're going to do next is called a bubble point calculation. So I want you to click on that. And when you do that, the software is going to add a new grid category or a grid area called calculation parameters. In there, it's going to ask you, okay, you want to do a bubble point. It's a thermodynamic function. Do you want to fix temperature or do you want to fix pressure? In other words, do you want to do the bubble point pressure or the bubble point temperature? Right now, the default setting is to calculate the bubble point temperature. Okay, but if in fact you clicked on that down arrow, you can see you can do pressure instead. Okay. Also, while it's set to bubble point temperature, I want you to notice that the default setting for the temperature, which is 25 C, the font color is now green. What that means is that the software is using that temperature as an initial guess because it's going to actually calculate that bubble point temperature. Likewise, you can change temperature to pressure, and now the pressure font is green. All right, let's just press calculate with the bubble point temperature. So we're going to do bubble point temperature calculate. And what the software is doing is it's going to create a very small bubble on top of this liquid. And then it's going to count, so it knows how many moles of vapor there is, and it knows how many moles of liquid there is. Then the software is going to adjust temperature until that amount of vapor is calculated. So in other words, it's kind of like adding a controller. I'm going to set the vapor to essentially 10 to the minus 9 moles. It's a little bit more detailed than that. tell me what temperature I need to have this calculation at in order for this amount of vapor to be present. Okay, so you can see here, in fact, this vapor amount is 10 to the minus 10th of the total amount of the system. So we use that's how we calculate a bubble point. We set the vapor liquid ratio to 1 over 10 to the 10th. Now we got that set. We say, okay, what's the temperature required in order to achieve that? And you're going to notice that we're going to do that multiple times. There's a dew point calculation. That's essentially the flip-flop of that. There is a vapor fraction calculation, and there's a vapor amount calculation. All four calculations use the same type of logic. Set the vapor amount or set the liquid amount relative to the total, and then tell me what temperature or pressure is required for that.
AJ, in this case, when let's calculate the temperature still at 25 C, does that connote that will be the guess was? Am I saying this right? Okay.
Yeah. So the temperature here is 25 C, but look in the summary section. Does it show 25 or 64?
Okay, I see it now. 64. Thank you. Yeah. So it doesn't change in that green area, change in the summary. Okay.
Yeah. Now, but here's a good point though, right? So it gives me an opportunity to explain something else. This grid here is our input grid. This is what we're starting with, right? And we always need a way of saying, well, what's our reference point? Even thermodynamics has a reference point. We're saying, okay, what did we start out with, and where did we end up? So this grid here shows us where we started. And in fact, if you look in the lower left here, it even says input. If you were to click on output, then in fact you would see the new temperature.
So the 25 is just I mean, is it just arbitrary then?
Yeah, well, that's the default setting because that's standard conditions. So that's just the initial guess. You can always change the initial guess. And in some cases, it's really important. You could have a very complex system that's hard to find the global minimum. So you may, in fact, want to start with an initial guess, or maybe even a better initial guess than what we did there.
Okay.
But that depends upon the application that you've got. In some cases, the calculation's real robust and it can find the global minimum with no problem. Other times, not so easy.
AJ, I have another question, if I may. So often with these bubble point calculation or or dew point calculation, sometimes some species did not react 100%.
Mm-hmm.
I'm talking from a stoichiometric point of view. Is there any way, it would be very interesting, at least for us here, to know the unreacted species, like you have acetone and water here, some of it will go into vapor space and some of them maybe will stay, in equilibrium and the liquid stays. Is there any way we can find out that?
Yeah, in fact, there are two ways of answering that question. One is, again, if the system goes to equilibrium, then the short answer is go to the report. And in your case, go directly to the element balance. And it'll tell you, well, in this case, we just have a very small vapor phase. So virtually everything is still in the liquid phase. But nevertheless, here you can see how much acetone remained in the liquid versus going into the vapor. Okay. The other way of answering your question is mass transfer limitations. Is that the system, even though it evaporates, there's mass transfer limits, because CO2 is a perfect example. It's like it's the poster child of poor mass transfer. Your system may be at steady state, but you may be far from equilibrium with respect to CO2. And under those cases, this tool isn't the right tool to predict, let's say, mass transfer limits. We'd want to use some sort of process simulator tool for that.
Okay, I guess more to discuss there.
Yeah.
Thank you.
You bet. Yeah. Okay. It's already 10 past the hour. Let's go ahead and break right now. We're going to come back at 15 minutes past the hour, and then we're going to get started again. And we're going to do a dew point calculation, and then we're going to do a couple of vapor fractions, and then we'll be done with this. So we'll see you guys in about 7 minutes. Okay. All right. 15 minutes past the hour. We'll get started again. Make sure everybody's here. Just show of hands. Is there a hand raising thing just to show that you're here? Great. Thanks, Brett. Great. Okay. Everybody else? Thank you, Joaquin. Dino and Xinjiang, you're back?
I'm back.
That's great.
Yeah.
That's cool. So just Dino, then it may not be here. Okay. Actually, I want to make sure he's here for the next step, because the next step is just another skill instruction that I want him to do. Well, you know what? We should probably be, okay, there's recording. Okay, good. So we're already recording, which is good. That way, if there's anything that's missing, you guys can go back to it. All right, we did the bubble point calculation. The next thing we want to do is a dew point calculation. And rather than, do everything all over again, because we pretty much know what you're going to do next, right? You're just going to flip from a bubble point to a dew point, put everything in the vapor phase, get a little drop that forms, and calculate that temperature. But rather than go through all the effort to build the chemistry model and add a new single point calculation, what I want you to do is actually just copy what you currently have. So if everybody would click on the bubble point object, right? You should have everything named now. Isothermal flash, bubble point. But click on, make sure that bubble point is highlighted, and then right mouse click on it and select copy. And then go to the back to the top level stream. Right mouse click and select paste. Doing that, you now create a new stream and calculation object identical to what you just created a minute ago. What you're going to do now is you're going to rename it, call it dew point instead. You'll go to the single point calculation underneath it, change the calculation type from bubble to dew point, and then press calculate. Now the actual values are not that important, but I do want to at least go through, what the software did with you. Okay. So now what the software has done is it's put everything in the vapor phase essentially and said, okay, I want 1/10⁶ of the total moles to be in the liquid phase. So if you look here in the aqueous, you can see that you got 5 e to the -5 moles, which is essentially 1/10⁶ the amount in the vapor phase, or really the amount in the total system. Okay. That becomes essentially the first drop of water. And then again, just like before, the software is calculating what temperature is required to achieve that state, right? That phase distribution. Okay. And the interesting part you have to want to notice here is that because you've added a more volatile material like acetone, right, the dew point of this liquid is now 93 degrees Celsius. By comparison, if it were pure water, that dew point would be 100 degrees Celsius. And so we can see what's called the dew point depression because of adding a second component, in this case, a component being more volatile. Same's true with the bubble point. The bubble point of water is 100 degrees Celsius as well, pure component, right? But because you added the acetone, that bubble point dropped to 64 degrees Celsius. Again, boiling point depression. So again, there's always thermodynamics that can be the physical chemistry stuff or the general chemistry stuff that we learned in university is always happening in the software. It's a matter of whether or not you want to think about it or look for it. Okay, you don't have to look for it. That's our responsibility to make sure it works. But there's always things to look at or learn about if you're curious about it. All right, good. So at the dew point again, now everything's in the vapor phase. We have a small amount in the liquid phase. We could look at the report. Again, you're not going to see a whole lot new here other than the fact that everything is in the vapor phase. Right? You can see 99.999% is in the vapor phase, only a small amounts in the liquid phase in this case. But that's okay. We don't care about it in this case. We're going to care about it in the next case. Good. Any questions then about either bubble point or dew points. Essentially, these are the phase envelope calculations, right? If you think about it, we're just at that envelope. We want to see what things look like either slightly above the envelope or slightly below the envelope. Okay, good. Let's keep on going with this. The next calculation we're going to do is called essentially a, wait a second, why don't I see that here? Yeah, okay. The next calculation we're going to do is going to be called a vapor fraction and a vapor amount calculation. What I want to do is now, rather than just look slightly above or slightly below that phase envelope, I want to actually look what's happening when you have two phases of reasonable quantities. Okay, so for example, let's say I wanted to look at the acetone water mixture when it was 50-50, 50% in the vapor, 50% in the liquid phase. How do we do that? And there are two ways we can do it. We can either do it as a fraction of the material or the total moles of the material. Okay. So this is actually getting into what you engineers would have learned in distillation. I'm not an engineer, I'm a scientist, so I've learned it for different reasons, but I can see this actually being part of the engineering training that you guys would have had in distillation. So let's go ahead again and add a stream. And let's rename the stream vapor fraction / amount. Good. Now what we're going to do here is we're going to use a different material. Let's use methanol instead, just to mix things up a little bit. So type in methanol. And once again, let's make this 40 moles of water, 10 moles of methanol. Now you're going to add another single point calculation. And that calculation type, and notice, by the way, immediately I stay in this upper right section because the next step is to select the type of calculation I want to do. And the type of calculation is going to be the fifth one down, called vapor amount. And I'm going to set that vapor amount to be essentially 25 moles. Let me explain what I'm talking about here. Okay, I've got 50 moles total in the system. I want 50% of it to be in the vapor phase. So by clicking on vapor amount as the calculation type, the calculation parameters shows up here as being, okay, you want to do a vapor amount calculation, you have to specify how much material is going to be in that vapor phase. And the material, the units in this case are moles. Okay, software thinks in moles again, remember. So that's why we show it this way. That's why I didn't change the units. We haven't changed the units yet. Go ahead and press calculate. When the calculation's done, you look at the phase amount in the summary section. Again, make it a habit. Always look at the right-hand side after you do calculation, just to see what the important stuff is telling you. You got a 50-50 mixture, liquid versus vapor. The temperature for the state to exist is 90.586 degrees Celsius at atmospheric conditions. Also look at the pH, 6.17. Chat about that in just a second. Let's look at the report now and scroll down to the bottom of the report to the element balance. And more specifically to the distribution. Okay, so we're looking at this table here. What's interesting to me, at least, when I look at the methanol, right, I've got 10 moles of methanol in the system, 8.3 moles is in the vapor phase, 1.7 moles is in the liquid phase, or essentially 83% of the methanol has vaporized, right? Compared to what about 41% of the water. So we certainly see in this 50-50 liquid vapor mixture a concentrating of the methanol into the vapor phase. AKA, we got a way of separating this through distillation. So I start putting multiple stages together on this. I can separate methanol from water until, if there's an azeotrope, until we get to an azeotrope. I'm not sure if there's a methanol water azeotrope. Let me stop there. I sort of went much faster here because you already understand the basic mechanics. And now what I'm focusing on is what the software is telling us in the calculation. Any questions about this type of, let's say, vapor fraction or vapor amount calculation? All right, let's do this one more time. I want you to go back to the definition tab. We're going to stay in the single point calculation, change the calculation type from vapor amount to vapor fraction. Now what you're going to do is put in 50 mole percent in the center here. So we've changed it to vapor fraction. Once again, the software says, fine, you want to do a vapor fraction. What fraction of the material of this 50 moles do you want in the vapor phase? And you're just going to put in 50%. And as you expect, you're going to get the identical answers. So you're going to get 25 in the water phase, 25 in the vapor phase, and you're going to see the same distribution of methanol and water in the two phases. Okay, any questions then about the what we're going to call the phase, the thermodynamic part of the calculations, where we're either doing an isothermal flash, or doing a phase envelope calculations with bubble point or dew point, or we're doing a vapor fraction or vapor amount calculation. Okay, then let me just go ahead.
AJ, I have one question. I'm sorry if you know.
Yeah.
Is there any way we can do an example with radicals, such for example, amines or carbonate species, ionic type species?
Oh yeah. Yeah, that's going to come
Yes.
next. Yeah. So what
Okay.
we've done at this point, in order to keep things simple as we train, is that we just do molecules, just to get you an idea of how the software works. Now, if you noticed, at the type of calculation, we're going from what we normally call thermodynamic types of calculation, where we're changing temperature, pressure, or volume, to where we're going to start changing compositions. So as we walk down this list, we're going to be doing like a set pH calculation. And we're going to do a set pH calculation with carbon dioxide and with acetic acid. And what you're going to see there is the buffering of the acetic acid or carbon dioxide to limit pH changes as I'm adding acid or bases. Okay. And again, so look at this next one we're going to do, and then the following one, precipitation point, and see if that's enough of the ionic chemistry for you. If not, then when we get to the water analysis, where we're actually adding cations and anions, including bicarbonate, acetates, etc., you can see that chemistry as well. All right, well, let's actually jump to that right now. Let's go back to the top level stream, add a new stream, and call this one set pH. Okay. And this one here is going to take, this is going to be interesting. What we're going to do is we're going to add carbon dioxide, of all things, right? You just asked about that too. Sodium hydroxide and hydrochloric acid to the grid. Again, we're staying with molecular flows for now, because we're waiting to do cations and anions when we get to chapter 4. Okay, we're still in chapter 2 right now. Okay, what we're going to do is we're going to add essentially.
Sorry, AJ, I didn't mean to steal your thunder. I apologize, but just was curious. That's all.
No, that's actually perfectly fine, because a lot of the stuff we show in the training, the calculation's practical, but the chemistry is not. But we try to keep the chemistry simple, so the chemistry doesn't get in the way of learning the interface. So so we'll notice purposely we're limiting the chemistry of what we're doing, because there's already enough to learn in the interface. Okay, let's now do this one here. We're going to add 1 millimole. Essentially, it's 44 milligrams rather, of CO2 into water. The idea here is that we want to see what the speciation of CO2 looks like when we change the pH. And we're going to do a couple of different pHs. Okay. So the system is carbon dioxide, water, and then we're going to use hydrochloric acid and caustic as the ways of adjusting pH. And the way we're going to do this is it's always trying to teach the chemistry with the mechanics, But again, try and keep the chemistry simple, but for now. What we're going to do is we're going to do this at without adjusting pH to 4, adjusting pH to about 8, 10, and then 12. Okay, so let's do this. Let's go ahead and just add, what we're going to do is we're going to add a single point calculation. Again, chapter 2 is all about single point calculations. When we get to surveys, we'll be in chapter 3. When we get to chemical diagrams, we actually don't have a chapter for that. That's kind of like a custom training class. When we do stability diagrams, that's chapter 6. Corrosion rates, that's chapter 7. Okay. So in this course, we're doing chapter 2, chapter 3. And then when we get to it, we're going to be doing chapter 4 with the water analysis, chapter 5 with the mixer. Okay. So there's a procedure that we're following here. So from now on, for the rest of the day, we're just going to keep on clicking on add calculation single point. Right, cool. So we're going to add a calculation single point. Okay. Once again, I'm looking up here. What have we got set up? Right now it's isothermal. Okay. I do want to change this to set pH, but not yet. Let's start by just pressing the calculate button. I want to see what the natural pH of this water is. So essentially I've got 44 milligrams per liter of CO2 in water. And when I do the calculation, the software says the pH of this water is going to be about 4.7. Okay, at 25 C in 1 atmosphere. Keep that in mind. So the software, because next thing we're going to do is we're going to be adjusting pH. And I think we'll just start at pH of 8 in this case. Now the software needs to know if I need to add acid or a base to the system. So in order to know that, the software has to say, okay, well, what's the starting pH? Once it sees it's 4.67, it knows it has to add a base. And so when we do our next calculation where we set pH, you're going to see that the software is given an acid and a base to use. But in order to know which one to use, it does this calculation first. So we now know that the base pH of the system is 4.67. Let's now change the calculation type from isothermal to set pH. Like I said just a second ago, the software adds acid and base automatically, the strong acid and the strong base automatically to the calculation. Now, we told it to use caustic and hydrochloric acid, but it would have found it anyway. You didn't need to add the caustic and HCl. The software would have defaulted to it. But what the software is also going to ask you to do is set the pH that you want. So I'm going to set the pH to 8.33. Now, you may ask, well, why 8.33 or why 8.3? Right? As it turns out, 8.3 is roughly the pH where the system is dominated by the bicarbonate ion. Okay? Essentially, we'll show this Thursday when we do surveys, but the bicarbonate system, essentially at a pH of about 6.3, the system is 99% CO2. At 8.3, the system's about 99% bicarbonate. At 10.3, the system's about 99% carbonate minus 2. That's essentially the speciation of the carbonate system. But let's just actually run this now. We got the pH to 8.3, hit the calculate button. Again, take a look over here. The curiosity is, well, how much acid or base was required? Sure enough, the software said it needed almost exactly 1 × 10⁻³ moles to convert this CO2 to bicarbonate. And you think about it, that's almost stoichiometrically accurate, perfect. Okay. The system is still only water. There's no vapor, there's no solid. But what we should now expect when we look at the speciation table is that if I added 1 millimole of caustic to the system, then that CO2 is going to be in the form of bicarbonate now. Let's go to the report. Take a look at some of the properties. There's my 8.3 pH. I've got 25 C in 1 atmosphere, as I know. Go down, maybe some more information that I'd be curious about, but not really here. We're just going to go right to the speciation table. And now this here, and I'm hoping this here is kind of like what you were looking for. This is telling us how the materials are distributed, the cations and anions are distributed in the water. I'm sorry, or what the composition is in the water. Remember, I added 10 to the minus 3 moles of CO2, 98% of it, right, is as the bicarbonate ion. You've got a little less than 1%, or maybe about 1% is as CO2, and another 1% that's as the carbonate anion. So at 8.33, we can see how the system has now distributed itself. And then, of course, there's some hydroxide and acid present, as well as some complexes. But those complexes are very, very weak. So we can pretty much ignore those. Let me stop and ask, when you ask the question about like different types of ionic systems, is this what you were looking at, or are you considering something else? Did you have something else in your mind?
Close.
Right?
Yeah. Yeah.
Oh, Dino,
Close
it was
is-
you who asked. Okay. So
Yeah. Yes. It's me. Yeah.
okay, then tell me what
Sorry.
you're looking at, because we can do it right now together. I did want to show this, but we can diverge from the training class. What are you thinking about?
I'm thinking more, I'll give you an example to illustrate my thoughts, AJ. So if you have, for example, a sour water system and you inject amine, let's say MEA, for example, okay, a significant portion of that will react to terminate, and it will produce some acid sour species, and there is a remnant of the MEA ion that is still in the water, and some of it will be entrained in water and hydrocarbons. So the idea is to determine how much of that MEA is percentage mass, or percentage mole in this case, has gone unreacted or stoichiometrically unfulfilled, if you will, for the lack of a better term. This is very close to that. I see that.
Yeah, but let's try your way though. I'll interrupt you there, and let's give it a try.
Okay.
You guys, everyone on the class is small enough to where we don't have to go by the book. And
Okay.
as long as we learn the basis, now we can actually extend it to do something that's more practical. So Joaquin and Brett, also keep in mind, if you want to look at something that is consistent with what we're testing, let's just try it out. So this is what we're going to do. We're going to stay with this idea. Okay, we don't have to do a set pH, but what we are going to do is acid-base chemistry, because that's what you're describing. But
Yep.
we're going to make it 4 phases. We're going to have a vapor phase, a hydrocarbon phase, the water phase, a potential solid phase if one forms, probably not. Okay, but we're going to add CO2 and H2S, methane, and maybe let's say a decane to the system. The CO2 and the H2S are going to partition to the 3 phases. And then we're going to add a little bit of MEA to it. We're going to see how all those components partition across the phases.
Perfect.
Very simple case. So let's do this. Everybody together. And let's add a new stream. Right? Let's just call this multi-phase. I'm not very imaginative with my names today. We'll just call it multi-phase. And right now, I want you guys to still work in mole units, even though it may not be natural for you to work in moles. Right now, the good thing about moles, if you're not familiar with it, is that moles make life easy when you're doing acid-base reactions, because you know that 1 mole of acid will neutralize 1 mole of base, kind of thing. It's like the stoichiometries. Eventually, we'll get to the more practical units like concentration or parts per million, whatever you're using. Okay, let's start with the hydrocarbon phase. Let's type in C10, H22. Okay, that's decane, normal decane. And we're going to add 10 moles of that. And in fact, what we're going to do is we're going to make the water 50 moles as well, just so we have essentially even numbers. Then you're going to add CO2. You're going to add maybe 0.1 mole of that. H2S, 0.1 mole of that. Oh, I forgot the methane. Then add methane. CH4, let's add, I always want to use 10, but I don't want to evaporate too much. Let's add 10 moles of methane. Now, one of the things you may or may not have noticed is that when you added the C10H22, the decane, to the water, the software identified that as being a hydrocarbon phase, and it automatically turned on the L2 button. If you'll just go back to the other calculations, you'll notice that the L2 button was not selected because we were doing largely inorganic chemistry, or if we were doing the organic chemistry with the methanol and the acetone, since those are miscible with water, there was no need to think about a second phase. Okay. We keep the second phase off, and Jingzheng, you can actually probably better explain this than I can. In the past, we've kept it off is because it just slowed down the calculation. If it wasn't going to form, why add extra baggage to the calculation? And that was really important in like the 90s when you only had maybe, 64 kilobytes of memory. So why add more equations if you didn't need to? Now I think we can probably add it on, but Jingzheng, is there any reason why we would still keep it off? Because it's still by default off in the system.
I'm not sure about this. So yeah, I think the L2 phase. When I work on this, I'm not sure if we have this kind of memory issue that maybe like decades ago due to legacy software, legacy code. But so far, I think we don't have this problem. I don't have knowledge why this is not enabled or not. Yeah, but so far we don't have this memory issue. Yeah.
Jingzheng, if you turn it on and turn it off, the calculation may take 4 seconds instead of 3, right, or 2. So who cares at that point? It's seconds, I suppose.
Yeah.
Yeah. Jim, we may actually bring this up with Jim and Chris just to find out is it time just to always keep it on, or are there other solver questions, reasons to keep it off?
Okay. Yeah, I will look into it. Yeah.
But what you're saying, AJ, is it will automatically come on in case we input hydrocarbon species and element there, correct?
I think so. I think anything above C4, it turns on automatically.
Okay.
Yeah. Okay, cool. All right, so we've got the stream here, right? Again, the first step is to do a calculation. And again, all we're doing right now are single points. So click on single point. And notice, by the way, we haven't added the MEA. So we'll do that in the next step. Add your single point. Okay. Now, we're not going to add MEA yet. All I want to do right now is just have us flash this system at ambient conditions, just to see where things are distributed. Okay. Then we're going to redo the calculation with the MEA. So press the calculate button and just confirm that we have 3 phases present. Okay. You can see, in fact, here that the water is less than 50 moles, vapor is more than 10 moles, second liquid is more than 10 moles, which means to me that, if everything was starting at the aqueous phase, we've had partitioning to the other phases. Now let's take a look at the report. And my preference is always to start at the element distribution when I'm looking at multiphasic systems. It just gives me an idea of where things are located. Okay. So now you can see you've got in the element distribution, you got 3 phases here, liquid 1, vapor, liquid 2. The methane, 99.5% in the vapor phase, 0.5% in the liquid. Here the CO2, or the H2S rather, again, S-2 is the H2S. Because again, we're looking at it from the key component or the key material code in that system. Okay, 3.7% is in the oil phase, 95% is in the vapor phase, and 0.8% in the water phase. This is what I was describing before. When we do scaling studies or corrosion studies, our interest always is all multiphasic, because we want to find out if in fact the corrosion or scaling contributing components are in the liquid phase, or are they essentially sequestered out into the other phases, such that when we start changing properties or conditions of the production, if we're going to see this material go back into the water phase and therefore create things like corrosive environments or scaling environments. Okay. Again, this is not a scale chem class or upstream production class, so we'll leave that for now. But it is important to say, yeah, this is something we look at, we want the customers to be aware of, because multi-phase systems are always more accurate to study than just looking at a water phase. Okay. All right, good. So we can see here that most of the material is going to be in the vapor phase right now. Before we continue, let me just ask the question. Do you know rather, is it okay for it to be in the vapor phase, or were you preferring everything to be either in a liquid 1 or liquid 2 phase in your example?
Liquid 1, liquid 2 phase.
Okay, let's do this. Let's go back to the definition tab. Let's set the methane to 1 mole instead of 10. Okay, that way there isn't enough volume for the material to partition to the vapor phase. Now let's look at the report again. Scroll down. It's still too much. I still have 80%. Okay, it looks like we're just going to get rid of the methane altogether, because even though I dropped the amount of methane by a factor of 10, you still have most of your the CO2 and your H2S in the vapor phase. So, okay, bad idea. Go back to definition, set the methane to 0. I'll just make it an LLE, a liquid-liquid calculation. And now press calculate. Now what we're going to see, though, is if in fact a vapor forms simply because the partial pressures of CO2 and H2S are too great for either phase. Right? But in this case, no. We end up with just 2 phases because the H2S and CO2 is able to dissolve all into the oil phase. Now we go back to the report, confirm that. Okay, so what we see now is that about 15 and 17% respectively is where the CO2 and H2S are located in the water phase, while roughly 80 to 85% is in the oil phase. Do you know, will this work, or do we want to make any other changes before we add the MEA?
No, this is perfect. Thank you, sir.
Cool. All right. Now let's go to the definition tab. Add MEA, methanolamine. Ethanolamine, rather. I'm sorry, ethanolamine. Okay, that's going to be our neutralizer, or our amine in this case. Now, we can almost guess that if I've got 0.1 mole of CO2 and 0.1 mole of H2S, in order to neutralize that, I'm going to need essentially 0.2 moles of it. But rather than just add it stoichiometrically, I'm just going to come back to you again, Dino. Is there a certain amount that you want us to add? Do you want us to add excess, just enough, or not enough? Is there anything specific?
Let's start with 0.25, if you don't mind. Excess.
Yep. So we have about 20% excess then, right? 5 divided by 0.05 divided by 0.2. 25% excess, right? Okay, good. So now let's recalculate. Again, before we switch over reports, I'm looking over here. pH 8.6. Yeah, pretty neutral. Good. Let's take a look at the report. Now we may want to start looking at 2 locations: the species output table and the element balance. Depending upon what you're looking at, you're going to be looking at both. Okay. Let's take a look first at the element balance, because that's where we were a moment ago. If you remember right, we had between 80 and 85% of the CO2 and H2S in the hydrocarbon phase. Now with the excess of MEA, that's essentially been removed. Okay. Since CO2 is more reactive than H2S, it's more acidic than H2S, it's not surprising that the CO2 reacted was neutralized to a greater degree than the H2S. Okay. And then if we look at, and also just to let you know, there's a certain solubility of MEA in the oil phase, not entrained per se. This is thermodynamically essentially stable in it. And then when we look at the speciation, we can see that most of the MEA here, this is the MEA ion. This is what essentially has been neutralized by the acid. We added 0.25, about 80% has essentially been consumed. Right. H2S, we added 0.1 mole of it, 91% has been neutralized. The CO2, only about 55% has been neutralized. Okay. This, I'm not sure what this is. C3H6NO3. That must be some, that's interesting. I'm not sure what that material is. I'm sorry, guys. But that looks like it formed a different complex. The heck is that? C3. Looks like that might be a complex between the CO2 and the amine. Right? You've got the MEA has got two carbons, but this one's got 3. Interesting. Okay. Anyway, so what I should say is this is how the system essentially equilibrated. You've got all these acid-base reactive species that have essentially either been neutralized or still remains. Okay. Dino, I'm going to press on you again. What were you looking for, and do you see it here? And if you don't, let's talk about whether or not equilibrium models can actually calculate that.
No, I do see it, AJ. I was looking for the N-reacted MEA, which is I see in the element distribution under liquid 2, a minute amount there. Just was more interested in the hydrocarbon phase, how much would be carried over. That's a specific interest.
I see.
Don't want to deviate because that may be a problem in the near future or downstream. You know, so you made a comment though, a very interesting comment. You say this is not entrained, this is thermodynamically in equilibrium within the hydrocarbon phase. I guess the next question is that if contacted with water, even minute amount water, would water have high affinity for amines? Would that be still the case or become more of an entrained phase at that point?
Yes, so entrainment is a physical what's the word I'm looking for? A physical phenomena, right? Yeah. It could either be essentially just that you've got coalescent droplets, or there could be emulsions, and either one of those the software doesn't handle predictably.
Okay.
Yeah. If you use the flow sheet tool, you can add entrainment, but it's a user specified value. It's not something that OLI is going to predict. And
Sure.
we're not going to look at it. It'll probably be another decade before we start looking at stable emulsions in terms of what our thermodynamicists are doing.
Okay. Thank you.
You bet, yeah. Okay, good. How are we doing on time? Okay, good. We could probably have a time to get in 2 or 3 more calcs before we take our next break. So the case we just did here was our first step in looking at, I'd say, again, we're looking at chemistry, but rather than changing the temperature or pressure of the system, we're changing the composition of the system. We're fixing temperature and pressure and allowing composition to vary. Okay, so that's why I explained before that in our calculations, if you look at the 13 of them, the top sections here from isochloric to isothermal, these are essentially changes to the physical chemistry, temperature, pressure, or volume, or total enthalpy have changed. Okay, but the bottom set here, they're largely changes in the composition of the system. Okay, when you're looking for a solution to something. And we just finished the set pH. Actually, let's do one more set pH here, since we're in the multi-phase system. We added the amine to the system to get to a pH of 8.6, and it got to a pH of 8.6. But it's quite plausible that, in fact, the controller that is used to add the amine is set to a certain target pH, okay, or some other type of target. So let's do this together. Let's keep the same calculation in multi-phase, change the calculation type to set pH. Okay. Set the pH to 8.3. No, let's set pH to 8. But now, like before, okay, rather than using acid or base, we're going to use the MEA to do this work. But since we only want to add MEA, you're going to change the option for a single titrant from no to yes. We're going to use a single titrant. And we're going to make that single titrant MEA. So we set the calculation type from change the calculation type from isothermal to set pH, set the target pH to 8, change the titrant option so that we're using a single titrant, and then change that titrant to be the the base to be the MEA instead of the caustic or the HCl, and then press calculate. Okay, now what I want you to do is go to the output tab down here. Click on the output tab so you can see more clearly what the software did. And I want to explain what the summary section said. So like before, remember we added 0.25 moles of it. What the software says is all you need is 0.182 moles to get to 8 pH. Our initial guess starting point was 0.25. So essentially it says, okay, I've got to remove about 0.067 moles of that. So that's what it shows here. I needed 0.182. You started, the initial guess was 0.25, so I removed about 0.067 of it. Now I've got essentially my 8 pH system. So hopefully that gives you an idea that you don't have to, again, the titrants don't have to be the strong acids or the strong bases. It could be whatever your system is, the system is that you're testing. And also that you start with initial guesses, but these initial guesses get overridden, and that information gets essentially documented here in the summary section. Okay, good. All right. Now we're going to take a little bit of a sidestep, and we're going to change the units. We're going to go from vapor-liquid and liquid-liquid chemistry to start looking at inorganic solid chemistry, salts. So now we're essentially shifting our gears to actually change the chemistry and the type of calculation that we're doing. So what I want you to do now is, actually, before you do that, let me just ask, are there any questions at this point? Okay. By the way, I just noticed that Faisal, you joined us. Welcome. I know we're already 2 hours into it. At what point did you join? I just noticed that you're here now.
Sorry, I joined like around 10 minutes ago. Actually, I'm really sorry. Yeah.
Okay. The good thing is we have a we're recording the training class.
Oh, that's thank you so much.
Oh, sure, yeah. So you can pick up where essentially you're starting, let's say, right now, but you can always go back and see what you missed. Also, what I'll make sure I do, let me just save this file right now. This is Basic Studio. What's today's date? Feb 28?
28 Feb.
Okay, so what I'll do is after the class is over, I'll email you this file so you can see what you missed, and then
Yes,
you can either
please.
review it or try it yourself. Okay.
Sure, thanks.
Okay, so but anyway, my question is, before we start shifting gears and looking at inorganic chemistry, is there anything else that you guys were curious about, or had questions about with respect to what we've just finished? Okay, I'll take that as a no, as a hard pass. So we're now going to look at inorganic chemistry.